Welcome to The Explainer. Today, we're going to decode what is, without a doubt, the single most important device in modern civilization. I'm talking about the transistor. It is the tiny, microscopic heart pumping away inside everything digital, and we're about to find out how it makes this whole AI revolution even possible.
You know, we hear all the time about these massive AI chips, these complex neural networks, these huge data centers. But what's the fundamental piece, the actual physical building block that makes it all work? Well, it's not just a chunk of silicon. It's a device so incredibly small, it operates right on the very edge of physics itself.
To really get this, we've got to zoom in. No, I mean way in. We're about to go on a journey, peeling back the layers of a complete AI system until we get right down to its atomic scale engine.
So we'll start with the whole AI accelerator chip, right? From there, we'll dive into just one of its many processing cores. And inside that core, we'll find millions of simple logic gates. But finally, we get to the hero of our story, one single transistor. This is it. This is where the magic really happens. Okay, so what is this tiny thing? At its heart, it's a switch, a stunningly sophisticated switch with absolutely zero moving parts. You could say it's the purest form of an on-off button that humanity has ever created.
Now, this textbook definition is actually really important. It tells us we are not dealing with some little mechanical lever. Those words, electrostatically controlled and quantum transport, mean we're using electric fields to manage the flow of electrons based on the, frankly, strange rules of quantum physics.
The best way to picture this is to think of it like a faucet for electrons. You've got a source, which is where the electrons come from, and a drain where they want to go. The path between them is the channel, and the gate, well, that's the handle on the faucet. A tiny little voltage applied to it controls this massive flow of electrons, deciding whether they get to pass through or not.
And this captures it perfectly. These are the two states that create all of digital logic, a 0 and a 1. When there's no voltage on the gate, it's off. The faucet is closed, no current. Simple. But as soon as you apply just enough voltage, it snaps into the on state, and boom, the floodgates open and electrons rush through.
That just enough voltage has a name, the threshold voltage, or VT. It is the magic number. It's the exact amount of electrical pressure you need to put on that gate handle to flip the switch from a 0 to a 1. And let me tell you, everything in chip design revolves around controlling this value with insane precision.
So if these little switches are so great, why not just make them smaller and smaller to get more power? Well, for decades, that's exactly what we did. It was called Moore's Law. But as we got down to the scale of just a handful of atoms, we slammed right into a physical wall.
Let's go back to our faucet analogy. What do you think happens when you shrink the distance between where the water comes in and where it goes out to just a few nanometers? The handle, the gate, it starts to lose its control. And the electrons, well, they start to leak through even when the faucet is supposed to be completely shut off. Engineers call these leaks short channel effects. You've got all these wild quantum phenomena like Dibble, where the drain starts pulling electrons across all by itself, or a gate oxide tunneling, where electrons literally teleport through the insulating layer. I'm not kidding. The result is a switch that's never truly off. It's constantly leaking power, and that can lead to all kinds of computational errors.
So if shrinking things in 2 dimensions wasn't going to work anymore, the only answer was to go 3D. Engineers had to completely reinvent the transistor's architecture to solve this leakage problem.
See, the core issue was that the gate only had control from one side, from the top of the channel. It's kind of like trying to stop a pencil from rolling on a table by just pressing down on it with one finger. It doesn't work that well. The solution? Simple. Get a better grip. And that led to this brilliant invention, the FinFET. Instead of a flat channel, the silicon is raised up into a little vertical fin. Then the gate is literally wrapped around 3 sides of it. So we've gone from pressing the pencil with one finger to gripping it with your thumb and 2 fingers. The control you get is so much better, and leakage just plummets.
Which brings us to today, to the next evolution, the gate-all-around FET, or GAAFET. This is the state-of-the-art tech. We're talking about what's inside today's most advanced chips. In this design, the channels are these tiny horizontal nanosheets of silicon, and the gate material completely, totally surrounds them. It's the ultimate grip. It's like wrapping your entire fist around the pencil. This gives engineers almost perfect control.
Okay, so now we have this perfected quantum switch. Let's zoom back out and see how billions, and I mean billions of these things come together to create the insane computational power that AI needs to work.
So, you take billions of these advanced GAAFET transistors, and you combine them to make basic logic gates, your ands and your ors. Then, you use those gates to build circuits that can do math, like multiplier accumulate units. And finally, you arrange thousands of those MAC units into these massive, super efficient grids called systolic arrays. You might know them by a different name, tensor cores. That right there is the beating heart of an AI accelerator.
But here's the part that just blows my mind, the scale. A single, top-of-the-line AI chip today has over 100 billion of these unbelievably complex 3D quantum mechanical switches, all firing away in perfect harmony. It's just staggering.
So we've gone from a full AI system all the way down to a device that's measured in atoms, and then all the way back up again. And it leaves us with this huge, fascinating question. Now that our switches are about as small as they can physically get, what's next? Are we at the end of the road for computing as we know it, or is this really just the beginning of something entirely new?